So I'm going to present the Spark approach to safe and secure software engineering. Spark is a technology that we develop at AdaCore together with Altron. So short agenda, I'll start with what are Spark formal verification tools, what they provide, and very quickly behind what is the Spark programming language which allows such analysis to be performed. Next, something very important for application is how we define various levels of software assurance and how they are adopted in industry. And I'll finish with a quick tour of what program-proof technology is today, and I'll conclude. So what are formal verification tools? There are two kinds of analysis in the Spark toolbox. The first one is called flow analysis. So you have a signature for procedure here in Spark, which declares its parameters. So you have input parameters, output parameters. There's an explicit mode. And you see there's a specification of effects. Indeed, with Spark, there's both an implicit specification of effects, for example, the fact that you don't want to read an uninitialized variable, and a possible explicit specification if the user wants to say so, with this global annotation, which adds to the signature of the procedure stabilize what global variables are inputs to the procedure, what global variables are possibly read and modified, so this in-out mode. Based on these implicit and explicit specification of effects, the flow analysis part of Spark will check that the implementation of the procedure matches the intent, matches the specification. Otherwise, you'll get messages. The second analysis of Spark is called proof. Again, it is the signature for the procedure stabilize, and we've changed the contracts. And again, there are implicit specification for proof, which is the fact that the code operates without errors, so no runtime errors, no division by zero, no overflow, whether it's integers or accessing beyond the bounds of arrays. And there's a possibility for users to specify explicitly the behavior of the services. So for example, here we add what we call a precondition. So that's a constraint on the color of stabilize with this word pre that specifies that the parameter mode should be different from off the special value. And in postcondition, there's something a bit more complex. There's a conditional expression here that says, in case of success, then we want a special change, which is encoded in this function delta change between the previous value of rotors, this notation rotors take old, and the new value of rotors, which is a global variable for the power applied to the rotors. Based on these implicit and explicit specifications, the proof part of Spark will analyze the implementation again and check that it matches the specification. Otherwise, you'll get error messages. So this is not new. In fact, program-proof technology, in particular with Spark, has started a long time ago, so in 1987. It has gone through a number of companies, and now it's co-developed by AdaCore and Altron, as I said. If you're interested, you can read the paper that I mentioned at the bottom, and there will be other references like that that you can find on the web for more information. And along the years, as you can see, I mentioned here just a few examples of projects. So C-130J, which is a big military plane, Tokyo Neo, which was a demonstrator for the National Security Agency, IFAX, which is the air traffic control over UK today, UN, which is a separation kernel, which was funded by the German security company Secunet, NVIDIA, which is using now Spark for their more secure software and firmware. So what is under the hood? Spark takes as inputs these programs in a subset of Ada, of the Ada programming language. And in this blue line, you can see what's inside the tool. So we translate the program into an intermediate form called Y3. And there's a technology called the Y3 platform, which allows to go to various provers. So there are logical formulas that are generated for all these proofs to be made. And we call under the hood these automatic provers at the bottom, AlterGo, CVC4, Z3. And you can see that there are other possibilities outside of the box that users can install if they want to go up to interactive proof, so helping the tool know more complicated facts. But that's for more advanced usage. And so this technology is all open source, and we could develop it with INRIA labs. So there are key features in Spark. The first one being the integration. So here I show one of the IDEs, the main IDE that we developed for our tools, which is called GNAS Studio. And you can see there's a Spark menu to run the various sub parts of the tool at various granularity on file, on actually subprograms lines. But everything is code. So what's important is that you can build, test, and prove all in the same IDEs. And in particular, you can see here that the contracts that I showed before, the precondition and postconditions, are just code. So you can build this additional specification in the code, and you can even debug them. So if they fail, you can test that they fail at runtime and already debug before you even try to prove the property on the implementation. A second very important feature is the automation. So what we strive for is to have this line where we can go as high as you want in terms of property complexity. So that's moving up in the graph, which entails going right in the graph, which means there's more effort on the user. It's more complex to prove more complex properties. So with the default settings, you can already prove variety of properties involving Boolean and linear integer arithmetic. As soon as you use more quantifiers, so when you quantify the properties of arrays and collections, as soon as you use nonlinear arithmetic with multiplication, division, modulo, etc., you will need more complex means of convincing the automatic proof tools that implementation corresponds to the specification. So that's what we describe here very quickly. And as you go with more complex properties, you might even need to program your proof, what we call ghost code, so code that is only here for the verification. And you can go up to very, very complex properties if you accept, in the end, to interact much more with the tools. And that leads us to interaction. So it's very important, even relying on the very powerful automatic prover technology that we have today, that the provers can give back feedback to the users when things don't go as planned. And so what the tool provides is a number of information about what has been done, what has not been done. And an example of that is a counterexample. The counterexample gives values for which the property which we try to prove here, a postcondition, is not proved, and possibly a trace and suggestions for a fix, etc. So that leads us to what language allows this kind of analysis. Because in fact, it's very important that the language is constrained to provide the sound basis for such a powerful analysis. So Spark is a subset of Ada. It inherits from Ada all the things you can see in the middle. So strong typing, the ability to do low-level programming, generics, object orientation, concurrency. And it excludes from that, on the left, those features that would make this kind of formal analysis impossible. So pointers that don't respect any kind of policy, ownership policy, exception handlers when you recover from exceptions, control types which have the destructors that are called when unwinding exceptions, functions that have effects on the global variables as they compute the results. And they add to the common subsets from Ada a number of specific annotations. So that's the thing on the right. That's purely additional to the code. That's not executable typically, and that's to specify properties that we want the code to respect. So a very simple example in Spark, the simplest you can imagine, if this procedure increments, you have the signature at the top. It takes as input and output this X parameter of that integer, and we can specify a number of things inside this what we call aspects. So data dependencies with this global aspect, which says there are no global written or read by this procedure. Dependencies with this depends aspect that says that the final value of X depends only on the input value of X. A precondition with pre and postcondition with post. So here we're just saying that X is input in input shouldn't be the maximal integer value, since we want to increment it. And in postcondition, we state that X has been incremented by 1. And below, you can see the body of this procedure where we increment the value of X. And what the tool can do here is that it can check that there are no runtime errors inside the body, and that all the data dependencies, flow dependencies, and the functionality are respected by this implementation. So that's a very simple case, but that's the basis for everything that's done on much more complicated cases. So how do we apply this kind of technology in practice? We have defined levels through which users go and select a given targets for their assurance. The first level is what we call the stone level, provide a strong semantic coding standard for your code. And the way to check that is that the program respects the legality checks. So the tool does that. And it enforces safe use of the language, that is, the concurrency is restricted. So that's what we call the Raven scar profile in Ada. And that expressions and functions have all no side effects. So procedures can have, but not functions which computer resolve. That in particular forbids language features that make formal verification impossible, like unrestricted pointers and exception handlers. At the next level, the bronze level, we check that initialization is correct. So all variables are initialized before they're read, and that the data flows as specified by the user, this is the contracts I showed before, are respected by the code. So it will detect problem with the reads of uninitialized data, problematic aliasing, even data races between concurrent tasks at this level. The next level is where we check for absence of runtime errors. We call that the silver level. So here it uses the proof part of the technology, and it will detect all kinds of runtime errors from division by zero, array out of bounds, all kinds of overflows and violations of range and specifications of types. The next level up is called the gold level. It's where people can specify key integrity properties of the software. So it uses the same proof technology, and here the user can specify properties on types, so using type invariance, or on controls, so on function and procedures using precondition and postconditions, as I showed before. You can also check at this level that OO is used correctly with respect to this principle known as the Liskov substitution principle, where derived classes implement a subset of the behavior of the parent classes. And the Graal, the ultimate level, is the platinum level, where you would prove full functional correctness. So that's very rarely used because this requires more effort. And that's typically the same kind of specifications, but up to the complete behavior of the program as at the goal level. You can also prove termination of loops and recursive subprogram at this level. So overall, you can see that there's this kind of pyramids. That's a good picture to picture these levels, where the full functional requirement level, the platinum level, is really at the top for a subset of the code. But beneath, there are a number of levels that we can reach, with the silver level in the middle being the target for all critical software when we can afford the cost. And of course, as you move up, you increase the level of effort and skills required. So how has this been applied in practice? We can draw here on the experience of Altran UK, which has been using Spark for decades now. And they have come up with this picture, which we published in the paper at the bottom, where for a given design assurance level or the equivalent safety integrity level, they apply a given level of assurance with Spark. So you can see that they have divided their projects in 3 buckets. In green, the high integrity level buckets for DAL A or B or SIL 3 and 4. The medium integrity level in light blue for DAL C, D and SIL 1, 2. And the low integrity level, so for DAL E and what we would call SIL 0 if it existed. So you can see that as they move up the level of these buckets, they will apply more and more costly and higher and higher assurance level in Spark. But the bottom line will be the silver level, which is the default level applied to all software which has some criticality when possible. So examples of use at Altran over the years are, for example, this Sholis project, ship helicopter operational landing information system, which was proved at gold level because there was some proof that the helicopter properly aligns with the boats at sea. The level can move up. So, for example, on the C-130J, this big military aircraft, initially data flows were proved when Lockheed Martin was taking care of this project. And later on, this project was continued by others, and some key properties were proved on the software, functional properties. IFACT is the air traffic control over UK, and it has been proved for absence of runtime errors, so what we call the silver level. And it continues now with the successor project for SITE, for military and civilian air traffic control. On the right, the tokeneer, so this demonstrator, all in open source, they can find on the web. It was produced for the National Security Agency, was proved at gold level, so key security properties were proved on this code, in addition to absence of runtime errors. And this reached the assurance level 5+, which is a quite high assurance level for security. So there are many more projects. What I wanted to emphasize also is that there are other tools based on Spark which use the capabilities of the underlying proof technology. So this record-flex technology is produced by a German company called Componolit, and they have a dedicated domain-specific language to describe protocol messages, binary protocol messages. And from that, they generate Spark code that is formally verified to comply with the protocol description and have no runtime errors. And the Spark code contains also contracts so that the user code can be proved at this level. To facilitate adoption, we've come up with a customer of this technology called Thales with implementation guidance. So to help people adopt level by level, moving up this kind of technology. And for each level, we explain in this booklet that you can find online the benefits, but also the impacts on the process and the cost and limitations, and how to go about errors that the tool, error messages that the tool provides when you're not respecting the constraints. And this booklet is this methodology is used by Thales in various teams and others to adopt this kind of technology. Just wanted to finish with debunking some myths about formal methods in general and program analysis at this level in particular. So some may think that it's only for math wizards. This is not true. This is really used today by software engineers. And the tools, so the main tool is called GuideProof, is integrated and is mostly automatic and fast. So there's a pickup time, of course, and it depends on the level. So based on experience with the customers, we've seen the level of 1 week for the bottom levels, more time for proving absence of runtime error, so up to 8 weeks. And if you want to prove more dedicated properties, then indeed it requires a few months of being on the job. But the experience shows that, in particular with Altran, they trained hundreds of engineers for this IFACT air traffic control software project, and that just worked. And recently, I attended a webinar by Airbus in Germany, where the question was raised about what training was advised, and the verification engineer on the job who was using Spark just said that for him no training was necessary because it's just a tool, and what you need is to be convinced, but not so much to be trained. So which shows how accessible this kind of technology has become. The second myth is that it's going to cost a lot. So there's indeed upfront investments, but what we've seen is that the use of this kind of technology decreases pre-test defect density. And such defects can have a high cost. So The lesson that we learned with NVIDIA, who has adopted now Spark for their most secure software and firmware, is that in the year before they adopted Spark, they had 2 security incidents that cost them 15 man-years combined. So for 2 incidents, 15 man-years, that's a very high cost, not counting the cost in terms of image. When you use this kind of analysis, you can also replace and lower some kind of activities, for example, low-level testing, for example, some review activities. And we have data here from Lockheed Martin on testing on the C-130J mission computer. They saved 80% of their test budgets by doing this kind of development. Finally, it needs to work on your environments. Today, Spark is available for Windows and Linux. We have cross compilation to a number of platforms, and even for platforms where you won't have an ADA compiler, we have in fact at the core code generator that generates C from Spark. And in general, Spark is interoperable with Ada, of course. It's the base language. There's also C, C++, Java. And really what we see is that mixed language development is the norm rather than the exception. So finally, a few words on proof technologies. There are a number of techniques that can be applied to code and other artifacts for developments. And there are also various points during the development where you have to recommend to design the code. And Spark is really at this bottom left corner where we apply what we call deductive methods, so using automatic provers to code. There are others in that area, in particular Pharmacy, which is applied to C code. And something that we share with the current Pharmacy is the intent to always be able to execute contracts, so annotations. So that's when you specify something, you can also test it and debug it. So this is a short history, but just to show that the general move is towards being able to specify and test the same thing. Finally, on this scale of being rather academic or industrial, there are various tools for program proof, and today Spark is the most industrial of them. I'll conclude with just a word with respect to MISRA-C. So Spark is a subset of Ada, so sometimes people tend to compare it with MISRA-C. They're really only comparable at stone level, so when we apply the very bottom of the Spark analysis, where MISRA-C will catch some typing violation, some conflicts or side effects, where Spark will really enforce these properties on the code. And at upper levels, what we get as guarantees at the bronze and silver level with respect to initialization and absence of what we call undefined behavior in C are really undecidable rules in MISRA-C and typically not enforced by tools. And upper levels, like gold level, is really outside of the scope of MISRA-C. So to conclude, in Spark, there are 5 levels of increased software assurance, from strong coding standard to full functional correctness. So you can stop at any level and get some guarantees. In particular, at bronze level, you get confidentiality. At silver level, you get absence of runtimers, which is a must-have today for secure software. You can always combine Spark with Ada and C at different granularities, and you can generate C code from Spark when you have a compiler for your targets. I'll finish with this number of pointers on the web for more information.